Well, I want to go ahead and get started because you know it's the typical thing in the term that we start later and later and later. So hopefully that won't continue to be the trend. But you can see that we're starting a new topic, and you'll notice this from a lot of our schema discussions from the last week and a half or so when we've been talking about entity relationship model. That there's a lot of different ways of representing any given schema. And so the question obviously arises, if there is a better schema or a worse schema or a better way of representing a particular data set or a worse way, how do we identify what that is? How do we even go about that process? So these were the goals that we talked about. We talked about these quite a bit last time. Well, the last few lectures is what I mean. So we have to have a complete representation. We need to be able to represent every fact that we may need to record. Users or customers having the same names is an example of that. Okay? That we need to be able to have a complete representation. Also, we want to be complete, but we don't want to be overly verbose. And so that's where this unnecessary redundancy comes from. We want to avoid unnecessary redundancy. It should be easy to manipulate the information. That's another great example of, like, what does it mean? What are the steps I have to take when I want to do this operation or that operation? So clearly I'd like to have ease of use. And then also we'd like to be able to enforce most constraints easily. That also is a really important thing. Although probably of all of those, the last one is the least crucial. Because we can always write software to do that for us. We can always write some software that checks the state of our database and make sure that it's proper. So we have this whole kind of classification mechanism that we can use for reasoning about database schemas. We call it normal forms. And normal forms are basically patterns that if a database follows them, then we consider the schema to be a good schema. Now that sounds really, abstract and generalized, and it kind of is. And I'll show you some of the issues that you have with normal forms, because you'll find that this is quite a different way of approaching schema design than what we've talked about. Because before we were like, okay, what are your entities? What are the relationships between them? Blah, blah, blah. And now we're going to take a very abstract approach. And so there's a bit of a disconnect from real world. And so I want to talk a little bit about that. But today probably won't be the best day to do that. We'll have to cover a little bit more ground before we can do that. The upside, though, is that normal forms can be formally specified, so you can reason about them, and that's really neat. For example, you can prove that something is a key. A candidate key on a table. So that's kind of a neat thing, is that you can actually prove that something's a key on a table. So yeah, our goal, design schemas that satisfy a particular normal form, and if the schema isn't good, i.e. we expect that it has some unnecessary redundancy, then there are simple rules we can follow to transform it into a normal form. Okay, and again, there will be some suspension of disbelief, which I will address at a future point. Okay, we have some examples here to just show you the kinds of issues that you can run into. So customer and, like I say, our customer details, customer ID, primary key, because we don't want to use names. That would be lame. And then we have loan with loan ID and amount, and we have borrower that associates customer IDs and loan IDs. We have a many-to-many mapping. We're doing this the right way. This is the way banks normally work. So notice in our example, we have 3 different customer IDs, but they all have the same loan number, because those 3 customers have a joint loan of some amount. It looks like in this case $10,000. Okay, so that's easy enough. That's no biggie. We could decide joins are slower than not joining. Remember, the databases are pretty fast at evaluating joins, but they're still slower than not doing anything. So what if we combine these 2 relations into a larger relation? So notice we've basically merged borrower and loan. I mean, this is basically exactly what you would get if you natural joined loan and borrower and then saved that into a new relation variable, bar loan, something like that. So notice customer ID, loan ID, the combination is a key, And then we also have amount. Okay? So yay, we eliminated a join. But the problem is, as you can probably tell, since we have a many-to-many mapping, we're going to have the same loan number appearing multiple times, and therefore we're going to have the same amount appearing multiple times. Does everybody see that? This is a problem. Why is this a problem? Well, what happens if somebody pays down the loan? I'm going to pay $200 against the loan. Well, now the amount needs to be changed from $10,000 to whatever, like I'm not even going to do that math in my head. It's Friday. $9,800, right? Did I do that right? We're going to pay $200, and now it's $9,800. Well, we have to make sure that all the places where L100 appears, that they also have that same amount, right? Irritating. This is a perfect example where a particular fact appears in multiple places, and if I'm going to make sure that all of the copies of that fact stay in sync, then I have to do more work. What a drag, right? So this is the challenge that we have with unnecessary redundancy. Now here's the question that I want you to think about. How do we know that there's a problem here? There's a lot of ways you could consider answering that question. And the one that I want to steer you away from is, we know that this is a problem because there's repeated values. There's repeated 10,000s, right? Because if you look at the example that I have now, you see that there's a couple loans with 10,000s. And we may have other loans with 10,000. The problem is not that a particular value is repeated. The problem is that we have this relationship between loan numbers and amounts. Okay? That's what I'm driving at here. Anytime I have L100 and amount in the same relation, well, then that amount should be the same if it's associated with L100, because it doesn't make any sense for our bank to have L100 and then different amounts. Everybody got that? That's really crucial. That's the important detail here. Okay? All right. This gets back to the question of what are we trying to model? And so if you were, designing a bank database schema, then one of the things you would sit down and realize is that loans should have one amount. Now we kind of take that for granted because we're all used to banking. Every checking account should have one amount. Every savings account should have one amount. So that's a rule. It's a rule for our specific enterprise. You could have another situation where you have different things, different behaviors associated with each. For example, customer IDs and loan numbers. Well, if we allow customers to have more than one loan, then customer IDs may be associated with multiple different loan number values. But we do know that if we have a loan number and an amount together, that the amount should always correspond to the loan number. Right? So if the same loan number appears multiple times, we have to have the amount appear multiple times as well. Okay, every loan ID corresponds to one amount. Now here's another way of saying it that's actually really important. It's going to become increasingly important as we talk about this stuff. If there was a schema, and that schema only had loan ID and amount in the schema, then loan ID could be it would be a candidate key on that schema. Okay? Everybody got that? So that's the rule. Loan ID and amount. If those two things appear together, we're expecting there will only ever be one amount associated with a given loan ID, so we can make loan ID a key on that schema. Okay? We call this a functional dependency. We say that one attribute or one set of attributes functionally determines another attribute or another set of attributes. And you see we write it with the arrow. Okay? Loan ID functionally determines amount. What we're saying is that for any time a particular loan ID appears, the amount has to be the same across all instances of that particular loan ID value. Okay? Any questions? This is really important because we're going to be seeing this for like the next 4 or 5 lectures. It also almost always makes an appearance on the wallet, and almost is an understatement. It always appears on the final too, so that's important. Okay, so we have Bor loan, and it has loan ID and amount. Notice we have that here. But you'll notice that even though we have this functional, so we have this functional dependency. It's because of the enterprise. Banks should be designed so that a given loan has one amount. And so loan ID and amount appear together in this relation, but loan ID can't be a primary key. Can't be a candidate key. Why can't it be a candidate key? Well, because we also have customer ID in there. And unfortunately, we have to allow multiple customers to be associated with the same loan. That's another rule of the enterprise that we're trying to model. Okay? Since this is the case, let me see, I think I say this here. We're going to have the same loan ID, and I should say this is a potential because, of course, you could imagine a data set where every loan was owned by only one customer, but that doesn't mean there's still not a problem, right? I have the potential for the same loan ID to appear multiple times in this table, and if the same loan ID appears multiple times, then the amount has to be duplicated because of this functional dependency. Okay? So we can use functional dependencies to identify potential circumstances with unnecessary redundancy. That's the big power of this stuff. That's why in the 70s, when people came up with this idea, they got super excited. Unfortunately, it didn't turn out to be as exciting as they hoped, but it turns out that even if you read like the modern SQL standard, the SQL 2008 standard or whatever, it still talks about functional dependencies because you can actually use those to optimize SQL, like a group by operation. You can optimize that with functional dependencies in certain circumstances. Okay. All right. Let's see. These are important, and they do have a lot to do with keys. I'm going to show you exactly how they relate to keys multiple times. But the idea is that functional dependencies allow you to tell if a schema design is a good idea or a horrible idea. And so it is very helpful to think about them during schema design. And so this is kind of the one thing that I want you to take away from this. People originally thought functional dependencies were going to be amazing, and they were going to basically make it so you could throw all your attributes into a bucket, throw all your functional dependencies into a bucket, push a button, and a schema pops out, like a perfect, beautiful schema. Well, the problem is that a lot of times the schema that would come out doesn't actually relate to real life very well. And so instead what you have to do is think about functional dependencies as you design the schema and think, am I actually violating any of the normal forms that I would like to satisfy? So they kind of become a tool in the same sense that design patterns become a tool guiding you when you write software. Things like that. So there's patterns that you'd like to follow, and you say, hey, that pattern's relevant here. Same thing with functional dependencies. Very good idea to consider them during schema design. Okay, so we can define these and reason about them. We're going to define them at a high level, but it turns out that all the formalisms surrounding functional dependencies are kind of boring and tedious, so we don't actually go into gory detail about them very much. Although if anybody's interested, I've never had anybody take me up on this, which is funny. But if you're interested, there's actually a big, thick book about functional dependencies that is old enough that it is in the public domain. And so you can actually get the PDF of the book online and read all about the gory details if you're curious. Okay, let's see. Here's another one. Large schema for employee information. Notice we have various people at our company, CTO, CFO, developer, tester, blah, blah, blah. We have their salaries, which, I don't know, these are older salaries, so maybe current salaries are much higher than that. We have start dates and so forth. And we say, you know what? This is a big table. I'd like to split this into multiple smaller tables. And so the question is, how can we or how should we split this table into multiple smaller tables? Like I say on the slide, the employee ID is unique. Everything else could be duplicates. Like we could have multiple Helens, we could have multiple Jeffs. Probably won't have multiple CTOs, although at a large company you certainly would imagine that you run into that situation. Certainly you're going to have multiple developers. Salary could be duplicated and so forth. So what if we split it into two? All right, well, so we've split it into two smaller, now this is just an example, right? We haven't really improved our circumstance very much as far as having large tables. And in fact, you probably can all look at this and say, wow, you actually made it worse, right? But the idea being that, well, why can't I just generate the original data? If I really needed to, I could generate the original data by joining the two smaller tables together. They still have some common columns, so I'll just do a natural join and get back the results. Okay? Is this a recipe for success or failure? I'm seeing thumbs down, right? Well, remember that I said the only thing that we can really guarantee is unique in the original table is employee ID. So what happens if I join together these two smaller tables? Is employee ID on both sides? Well, no, so I have a problem. Okay, any problems with this? Yes. And this is getting back to the same issue before of customer names, employee names not being unique, so they're not a good thing to use for a key. If you had a society in which every single person always was required to have a unique name, A, that would be quite interesting a society to live in. B, you could use it as a key. But we don't have that situation right now. So if you had this kind of a scenario where you have Mary the CFO, so she is an important person at the company, and then you have Mary the gopher who goes for this and goes for that, then, well, we have a problem, because if we join these two things together, each Mary gets doubled, and Mary the CFO, boy, I can't even talk, it's Friday, I tell you. Mary the CFO gets stuck with the gopher details, and Mary the gopher suddenly finds herself doing quite well, right? So this is a problem. We don't like this at all. This has a name. We call it a lossy decomposition. We took a table and we broke it into multiple tables, and we lost our minds. That's basically what happened. We lost our grasp on reality. So we don't like lossy decompositions. Okay? So we say that lossy decompositions can't accurately reflect all of the facts about the enterprise. You probably saw that very quickly. Mary the gopher with Mary the CFO's information, and Mary the CFO with Mary the gopher's information. So we want only lossless decompositions. You can specifically define what decompositions are lossless or lossy using functional dependencies. They allow you to reason about these things. Okay? So this is what we want. Okay, first normal form. First normal form is not that exciting. Basically, first normal form is already implicit in the relational model. We're basically saying that all attribute domains must be atomic. They can't be divided into smaller units that can be manipulated. You know, sort of, you have a value whose components can be manipulated. Okay? You may wonder why that's a big deal, and it's not a huge deal, but it does add complications when you allow non-atomic domains. Okay? Now you may have noticed the entity relationship model allows non-atomic domains. Okay? Many SQL databases also allow non-atomic domains. So, but the relational model enforces this already. So that's why it's not super exciting to think about first normal form. First normal form is kind of a simple, basic form that the relational model uses just to retain sanity. That's how I would describe it. So yeah, here's a simple example ER diagram for magazine subscribers. You can see that we have 0 more email addresses. Remember that when we have a multi-valued attribute, it's a set. It's not a multi-set. So for a particular subscriber, they can have each email address they have is only allowed to appear once. Okay. And then we have a composite as well, address, street, city, state, zip code. Okay. Hopefully you all remember exactly how we translate this. It's really straightforward. The composite gets squished down, so we just take all the components and plop them directly into the subscriber relation. Notice we have sub ID as the key. And then sub emails, how do we deal with that? Well, we take the single valued version of the multi-valued attribute, which is just email address, right? And we plop that into a separate relation schema and associate it with sub ID. Okay? And, so you can see, this is one of those things you probably wouldn't indicate specifically when you're writing relation schemas, but notice how in sub emails I've underlined all the attributes. It's a bit overkill. You don't need any attributes underlined in that scenario because it's a set of tuples. It's not a multi-set of tuples. But the fact that each email address can only be, let me try to say this more clearly. A particular subscriber has a set of email addresses, not a multi-set of email addresses, is enforced by a key constraint on that table. Everybody got that? So that's the important detail. All right, any questions? Okay, so that's that. So like I was saying, SQL databases definitely support non-atomic attributes. Okay, and it can be really useful. If we have time, then I'll show you some examples from real-world databases that actually help out quite a bit. The thing is, don't ever use those things for keys. If you never use those things for keys, you basically avoid a whole bunch of trouble. So you will run into situations where it may really be a good idea to use a non-atomic attribute for a particular column. That's fine. Just don't ever make it a key, and you'll make your life a lot simpler. Okay? I remember one scenario where I was working for a company, and it was a bulletin board kind of thing. They had a database schema for bulletin boards where you could go online and ask questions. So you'd have forums and topics, and then topics would have threads, and threads would have messages. And you could click through that, and the system would remember what things you clicked through so that you could go back. You could go back, or you could see a list of the things that you had looked at recently. And the way that they stored it made me shudder when I saw it. They had this big varchar column, and they would basically capture every thread ID separated by commas. And this column would just grow and grow and grow. If you had like a really active session, then that column could grow to the point that it started getting truncated, and they started running into trouble with that. I was like, why are you doing that? That's terrible. There can be reasons, and there can definitely be reasons not to do that too. Okay, so composite types, address, blah, 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 multi-valued, yeah. So we'll talk about that more in the future, but you can look at that later if you want. Okay, other normal forms. So these forms use functional dependencies. Okay? So basically, we can use functional dependencies informed by what we're modeling, and we can use the schema design to decide if a particular schema needs to be decomposed. And keys are also a functional dependency. Okay, so let's look at this. The way to think about functional dependencies is similar to the way we think about keys. They are certain kinds of constraints. So you remember how I would have loan ID, branch name, amount, or balance, and or account ID, branch name, balance, that kind of stuff. The key imposes a constraint on what tuples can appear in a particular table. And so functional dependencies operate in a very similar way. And like I say, here's some more terminology for us all. We would like to constrain our database to only contain legal relation values. What that means is that the relation value doesn't contain any rows that would violate any of the constraints. Okay? So we don't have two loans in the loan relation with the same loan number, because that would be an illegal relation value. So relation schema capital R. Notice that we're introducing a new variable. F, capital F, is a set of functional dependencies. So these might be from your schema design, your analysis of the thing that you're modeling. And so we say that relation R, or relation value R, satisfies F if R is legal. So we're saying that R has to conform to all of the functional dependency constraints in F. Okay? Another way of saying it, F holds on R. Now, when we say F holds on R, this is sort of a definitional statement. This is not a statement about a particular relation value. Because you notice that we're saying this about a relation schema. Capital F holds on capital R. When we say that, what we're saying is that there's a bunch of constraints in capital F, and the relation value of that type is only allowed to have tuples that conform to the constraints that are in capital F. Okay? The set of relations with R is their schema that are legal with respect to F. So basically, we're just saying we have a database, we have a schema, we have the set of constraints, and just imagine all possible database values, so relation value contents that conform to that set of constraints. All right, everybody got that? Again, just terms. So here's a formal definition of a functional dependency. You'll notice that we use Greek letters a lot in this part of the class because we need to represent these various sets of attributes. So we have one attribute set alpha and another attribute set beta. So alpha could be loan ID, for example. Beta could be amount. That would be fine too. And so, as the slide says, the functional dependency alpha functionally determines beta holds if you look at every pair of tuples in R, and if the alpha parts are the same, the beta parts are also the same. So imagine loan ID and amount. Again, you see two tuples with the same loan ID, then they need to have the same amount value as well. Okay, so this is a general statement of the functional dependency holding. All pairs of tuples T1 and T2 in R, if T1 alpha is the same as T2 alpha, then T1 beta is equal to T2 beta. Okay, so easy enough. Now, if we have a super key, remember a super key is any set of attributes that uniquely identifies tuples. It does not need to be minimal. Candidate key is a minimal super key. So if we have this kind of a situation where we have a super key, capital K, we can say that capital K functionally determines the entire relation schema. So K functionally determines R. And you'll notice that when we plug in K and R into our definition of functional dependencies, it just works. For all pairs of tuples in R, where the K attributes have the same value, then the R attributes have the same value. Okay, that's an unusual statement. T1R equals T2R. Basically what we're saying is the entire tuples are the same, i.e. they are the same tuple, because remember these are sets of tuples. Okay? So you can think of keys as being a special kind of functional dependency, or a functional dependency that applies in a specific circumstance. Okay? So we might have a situation in a table where we have a functional dependency where the left-hand side isn't a key because of other reasons. And that's fine. The functional dependency still states an important relationship between attributes in that schema. But if we can get a table with just the left and right sides of the functional dependency together in that one table, then we can make the left-hand side a key. Okay? All right, so bar loan. We have this functional dependency. Loan ID functionally determines amount. And so when we see a particular loan ID repeated multiple times, well, it requires that amount also be repeated multiple times. Okay? Bar loan also has another key, which is customer ID and loan ID together functionally determine the whole lot. Now I say here that it's a functional dependency that's not specifically required by what the enterprise needs to model. That's not precisely true. It's partially true. Because I mentioned that every customer needs to be able to have multiple loans associated with them, and each loan can be associated with multiple customers. So those rules by themselves suggest that customer ID and loan ID together are important, that they may functionally determine some other things. But then we can also take that detail and the fact that loan ID functionally determines amount to derive that other dependency. And we haven't talked about how to do that yet. We'll talk about that next class. But you can see that we have two functional dependencies that hold on this schema, and they're kind of in conflict with each other. Now, not really, but the quote-unquote conflict results in unnecessary redundancy. That's the issue that we have. We have unnecessary repetition of values. Now, there's a special kind of dependency. It's our favorite kind of dependency. It's called a trivial functional dependency. A trivial functional dependency is a dependency that holds on any relation value regardless of any values you happen to pick. You could pick any relation value you want, and that trivial dependency will always hold. Okay? And so, here is an example of a trivial functional dependency. A functionally determines A. Really obvious, right? Of course, if the A values are the same, then the A values will be the same. That's stupid talk, right? So this is an example of a trivial functional dependency. Basically, anytime you have, let me see if I have this on the slide. Yeah. If you have alpha functionally determining beta, and beta is some subset of alpha, an improper subset, it doesn't have to be a proper subset, then that functional dependency is trivial. Okay? Any questions? One thing that I want to mention, this is a big mistake that students make, and I know it's because at Caltech people love to throw around the word trivial, like, oh, that's trivial, it's so easy to solve, blah, blah, blah. I'm sure I did that too when I was an undergrad. But that's not the meaning of the word trivial here. Okay? The meaning of the word trivial here is it is satisfied by any relation value. Okay? That's what we mean by trivial functional dependency. It doesn't matter what relation value you come up with, the trivial functional dependency will always hold. So basically what we're saying is that this is a functional dependency that you can identify, but it doesn't add anything meaningful. Loan ID functionally determines amount. That's a non-trivial functional dependency. There are definitely relation values that don't satisfy that constraint. But if we have loan ID functionally determining loan ID, that's a trivial dependency. Any relation you come up with loan ID in it will satisfy that. Okay? There's a reason why I'm belaboring that, because when we get to the next way of refining this idea, we'll come across something else that's trivial. But it's definitely not simplistic. Okay? It's actually quite interesting. Okay? So just keep that in mind that we have a very specific meaning of the term trivial in this context. Okay, closure. So one of the things that you have to be able to do when you have functional dependencies, first of all, you'd like to have sort of a minimal set of functional dependencies, because why do I want to state everything? Like you'll see, oh, you've got a schema with 5 attributes, A, B, C, D, E. Well, what all functional dependencies hold on A, B, C, D, E? Well, you might say A, B, C, D, E functionally determines A, B, C, D, E. Yes, that's a trivial dependency. I'd like to ignore those. So what we would like to be able to do is have a schema and a set of functional dependencies and see what we can infer from them. So the example on the slide is a nice simple one. A functionally determines B. B functionally determines C. If we know those two functional dependencies hold on a schema, then A functionally determines C will also hold on that schema. All right? So you can see that we can infer dependencies from other dependencies. Now, if you were to take a set of functional dependencies F and figure out all the dependencies you can possibly infer from that initial set F, then you end up with what we call the closure of F. Okay? And we denote that as F plus with a little plus superscript. Okay? Like I say here, F plus includes F and all the dependencies that can be inferred from F. This also includes a whole bunch of trivial dependencies, which are not that exciting. Okay? So we're going to be using the closure of F quite a bit, but we're not going to talk about how to produce it until next time. So Boyce-Codd normal form is what I would say is the first interesting normal form. So remember we had first normal form. There's actually a second normal form, but we don't care about it anymore. You can read about it on your own if you're curious. Boyce-Codd normal form is a pretty interesting normal form because it's able to eliminate any redundancy that's identifiable by functional dependencies. So we have a relation schema capital R, set of functional dependencies capital F. We say that R is in Boyce-Codd normal form with respect to that set of functional dependencies. So obviously, you can't say something is in a particular normal form without knowing the set of dependencies that should hold. Okay, hopefully that is obvious. So all functional dependencies, alpha functionally determines beta. And notice we're saying that alpha should be in R and beta should be in R. It doesn't make sense to have a functional dependency that doesn't appear in R and worry about that. So we only care about the attributes that actually appear in R. Then at least one of these things holds. Either alpha functionally determines beta is a trivial dependency, or alpha is a key for R. If at least one of these things holds, then we know that that schema is in Boyce-Codd normal form. Okay? Now you'll notice here that I say alpha functionally determines beta has to appear in the closure of F. So there's the dependencies that appear in F, but then there may be additional dependencies in the closure that actually trip us up. And we'll see some examples of this as we go through this material. Sometimes that can be a little bit tricky. Obviously, if every relation schema is in Boyce-Codd normal form, then your entire database is in Boyce-Codd. This is a really desirable normal form. So Bohr loan. Notice we have customer ID, loan ID, and amount. And the combination of customer ID and loan ID has to be a key because we want to be able to have customers with multiple loans, loans with multiple customers. But we also know that there's a functional dependency that holds. Loan ID functionally determines amount. It's not a trivial dependency. The right-hand side is definitely not a subset. I'm sorry, the left-hand side is not a subset of the right-hand side. Okay? But we also know that loan ID by itself cannot be a superkey on this schema because we have another constraint we need to satisfy. So this schema is not in Boyce-Codd normal form. Okay? Now if you looked at borrower, notice we have customer ID and loan ID as the combo primary key on borrower. No matter what set of functional dependencies you came up with that apply to that table, they're all trivial, and or the left-hand side is going to be a key for borrower. Okay, so that's cool. Go us. And then if you have loan ID, and amount, well, yes, there's a non-trivial functional dependency that holds on that. Loan ID functionally determines amount, but loan ID is also the primary key of that schema, so we're good. It's in Boyce-Codd normal form. All right, any questions? You will have to do this, so if you have any questions, definitely a good time to ask. Pretty straightforward, right? Okay, the neat thing about Boyce-Codd is that it is actually possible to define rules to take a non-BCNF schema and turn it into a BCNF schema. So, like I say here, if R is a schema not in Boyce-Codd normal form, then that means that there's at least one functional dependency somewhere. We know it's not trivial, and we know that the left-hand side is not a superkey of the relation schema. So it turns out that you can take that relation schema and decompose it into two new schemas. Now, what goes into the new schemas? Well, it's on the slide. So if you have alpha functionally determining beta, that's the non-trivial functional dependency. Then alpha union beta becomes one schema. And then R minus the quantity beta minus alpha becomes the other schema. Now, I don't like this formulation because we have this formulation because alpha and beta could overlap. It turns out that it never overlaps for interesting functional dependencies. So really, we could just say alpha union beta and R minus beta, because beta minus alpha is just going to be beta. All right? So you can take that and you can decompose it. Now notice, alpha union beta. Is there a key now on that schema? Remember I said that a functional dependency has, if the functional dependency holds on the schema and only the attributes of the functional dependency are in the schema, then the left-hand side could be a superkey. So alpha union beta, you know that alpha is a superkey. Okay? Now, of course, this process may need to be repeated because there may be other functional dependencies that hold on R minus beta. So this is a process you iterate on until you know that every schema is in Boyce-Codd normal form. All right? Any questions about that? All right? So if we took bar loan and we said alpha is loan ID and beta is amount, then you can see that alpha union beta. So we take R and we decompose it back into, it turns out that it turns back into loan and borrower. So alpha union beta is loan ID and amount, and we know that loan ID is the key for that relation schema. And then R minus beta minus alpha is going to be customer ID and loan ID. Okay? So it turns bar loan back into loan and borrower, which is neat. Okay. All right, so let me just ask you this. Are there any questions at this point? This is the introductory coverage of functional dependencies for you. So let's go ahead and wrap up, and then we can all quit early because it's Friday, and everybody likes to quit early on Friday. So normal forms. Basically, these are guidelines for what makes a database design good. And the neat thing about them is that it is a formalism, so we can actually specify these things and reason about them. And you'll notice next time that you can get quite sophisticated in how you reason about them. But they're like a generalized version of a key. And this is kind of a neat thing. So we can actually use these to reason about keys. We can use them to identify redundant information. Okay? So constraints between attributes in a schema. Loan ID functionally determines amount. That's a special kind of constraint that we can say about our enterprise. We don't have to relegate that to just a single table. It's something we know is true across the entire enterprise. Okay? So we've covered first normal form in Boyce-Codd. First normal form is not that exciting. Just requires that all attribute domains are atomic. We already get that in the relational model, but SQL may violate that. Boyce-Codd uses functional dependencies, and notice it says that it eliminates redundant data. It basically eliminates all data that is redundant that can be identified through functional dependencies. Okay? So if we can state a functional dependency about it, we can reason about it using Boyce-Codd, and it will be effective. Okay? So that's kind of neat. So, but here's the question that we need to think about. We need to know how to compute the closure of a set of functional dependencies. We can easily state functional dependencies. Loan ID functionally determines amount. Maybe we can say loan ID functionally determines branch name as well. Account ID functionally determines balance. Account ID functionally determines branch name. So we can state this kind of stuff. That's no biggie. But we have to be able to take those functional dependencies and figure out the closure so that we can look at every schema and identify any functional dependencies that apply to that schema. So we need to know how to compute the closure. Okay? Second issue to think about. Does Boyce-Codd have drawbacks? And the reality is that Boyce-Codd actually has a couple of drawbacks. One is that it can't actually identify all redundancies. It can only identify redundancies that can be reasoned about using functional dependencies. Turns out that functional dependencies aren't the whole picture. The second thing that we run into is that Boyce-Codd actually has another downside, which makes it harder to enforce all of our database constraints. So next time we'll talk about third normal form. We'll talk about a lot of this stuff about how to reason about functional dependencies as well. So any questions? Alrighty, well have a good weekend. We're done.